for being here. My name is Corinne and I am the project manager for Beta Engineering, and we are proud to present our final design for the LaPorte Avenue and Silhavy Road intersection redesign project. Alongside myself today, you will hear from Hannah, our structural engineer, Owen, our hydrology engineer, and William, our geotechnical engineer. Today in our presentation, I will give you a brief project overview. You will hear from each discipline of Beta Engineering, and we will end our presentation with the closing, which will include our cost. So for the project introduction, I'll start with the location of this project. To no surprise, the location of this project is at the LaPorte Avenue and Silhavy Road intersection. This intersection is about 0.3 miles to the west of State Road 49 along LaPorte Avenue, and the surrounding areas you see residential areas and commercial areas. Now, I wanted to go over just a brief project scope as to why this project needs to happen. Why does this intersection need to be updated? First off, there needs to be an increase in capacity. Currently, the intersection is exceeding, there's too much demand for the intersection. Secondly, there needs to be an increase in driver safety. This intersection actually ranks third in Valparaiso for the number of crashes it sees a year. Secondly, we were tasked with designing a safe pedestrian passageway through this intersection, which will be done through a bridge. The geotechnical aspects of this project are designing foundations and pavement for the new roundabout. And lastly, the stormwater management systems for the intersection needed to be updated. So I wanted just to give a brief overview of how the current intersection operates. And a lot of you probably use this intersection and maybe even use it today. This is actually a still from drone footage of the current intersection. And just some things to point out that we're choosing to update with the intersection is, for one, to the east here, you can see this long queue of cars waiting to turn left. You can see the poor pavement, which I'm sure a lot of you guys are used to here in Indiana, unfortunately. To the south, you can see that just off the page, there is a car that's trying to turn left that's actually blocking the flow of traffic, and it backs up into the intersection. And lastly, you can see that there are no pedestrians using this intersection. So all of these things are going to be remediated in our design. So with that, I'd like to introduce the transportation part of this project. So why I chose to update this intersection to a roundabout, and a lot of you are probably thinking, why just redesign the intersection? Why even make it a roundabout? Well, for one, using a roundabout, it's safer. And as I said, there's a lot of crashes in this intersection. 30% of all crashes will be reduced because of this intersection. The crashes that do occur will be at slower speeds, and they will be more rear ends than they will be T-bones. Also, roundabouts also are quicker for a flow of traffic through the intersection. It's actually more efficient. And also, they're actually less expensive than typical signalized intersections because there are no hardware or electrical costs of the signals, and the long-term maintenance is actually lower. So here's our layout design for the roundabout for this intersection. Just some things to note: the alignment of the roundabout currently ties in really well with the current road alignment. There are brick medians, as you can see, on all four approaches. This will prohibit that left turn movement that I was talking about, so the vehicles can't block flows of traffic, which could then block the intersection. There's also a decorative median in the center, which we'll use to also help beautify the city. And also there's a truck apron that many of you guys probably know about, that way that trucks using the roundabout can mount the curb if they need to. Just some other things to note: that this gray box is the bridge placement that our structural engineer will talk about, and that it coincides really well with actually a roundabout design. And just some dimensions here that I put just so you guys can see, but all of them comply with the informational guide on roundabouts. So just to give you an overview, how will this roundabout operate? We have this roundabout. How's it going to operate for a motorist? One thing that's checked with roundabouts is the fastest path. Basically, when a motorist approaches the roundabout, they have 5 options of a turn movement to use in the roundabout. And we check to see what speed these vehicles will be traveling on based on the geometry of your roundabout. And really, all this just shows that for all the different options, a vehicle wouldn't be traveling more than 30 miles per hour through this roundabout, which is very safe. I also just want to show you just a quick typical section of an approach lane to the roundabout. Just some things to note: the lanes are typical 12-foot lanes. There's a slope on either side of them. There's a curb and gutter. There's a grass strip, and then you have the sidewalk. So all the pedestrians trying to get to the bridge around the roundabout are safely offset from the roadway. And with that, I'll pass it off to our structural engineer, Hannah.
Hello everyone, I'm Hannah Misch. I'm going to present the structural report. And to start the structural report, I'm going to give a background of what I considered before I came to the conclusion of my bridge, because you might see it and think that is kind of ridiculous. So starting with preliminary design, our design criteria provided to us is that it needed to be ADA compliant, and that's compliant with the state. It needs to be handicap accessible, but also they wanted us to have a maintenance vehicle, be able to access the bridge, to take snow off, clean it up and everything, but we ended up scrapping that criteria because it was really hard to design for. The bridges would have to be a lot bigger, wider, things like that to accommodate that weight. And we also considered safety, pedestrian safety, but also vehicle safety, location, connectivity, aesthetics, and constructability. So in this image, I included kind of a view of our area, what we're trying to connect to, where are the current pedestrian crossings that are safe, because as we know, our current intersection is not a safe pedestrian crossing. And then I also have in red the sidewalks, like the current sidewalks where people can walk now. So we really wanted to connect the neighborhoods to the shopping centers, which is kind of why I settled on my design. Some of the things we considered was a truss bridge with a ramp system. The ramp system is ADA compliant, but because the bridge had to meet a certain height requirement, the slopes up to the bridge had to be at least 5%, but you'd really like them to be smaller than that. So the ramp would have ended up taking up a very large footprint, so we kind of threw that out, and also we only would have designed one span, so you can only reach from one side of the road to the other, and I just didn't think that was enough for what we're trying to get accomplished. So then we considered a tunnel. The tunnel, it has a low level of comfort for people using it. Tunnels are usually dark, so you have to have them a certain size so people don't feel cramped in them and lighted and things like that. Also, the thing about tunnels is there's a lot of excavation involved. The construction would have been very extensive, and also, unless we wanted to do multiple tunnels, it only reaches one span. So this is kind of what I was looking at. I was like, we're doing a roundabout, so why not do a roundabout bridge? So I've never designed a circle bridge before, and it turns out I'm probably not going to learn that in my 4 years here, because that's like much more grad school than I can do. So I'm like, how can I reach all four sides and still have it look really interesting? So then I started looking at that bridge, and then also elevators to kind of fix the space issue with the ramps. Well, what I considered is 4 bridges. This is very constructible because it is one span, one single span, very long. We can construct each side one bridge at a time, only shut down one entry to the road. So it was kind of constructible. We could just tie the bridge into the columns very easily, and that way we can connect the elevators to, everyone can walk around the bridge to all the sides. Each span is 200 feet. In order to design this bridge in the time that I had, I made all spans identical. If we had more time, I would have been able to make some of them different. That way we could minimize the footprint a little bit, but that wasn't really, I couldn't do that in a semester, so this is what we did. So for like the material, I'm not gonna go too far into my analysis, even though that's what I spent my time on, because that's not really gonna like appeal to my audience. So we're going to talk a little bit about the aesthetics. I chose HSS sections, which are like squares or rectangles. That way the bridge has a really clean look. If you go back originally to the bridge design, that arc's actually very slim. From the top of the bridge deck to the top of the arc, it is 10 feet. That's not a very tall arc. So I wanted to keep the entire view of the bridge very slim and appealing. That way it's not hugely distracting for the drivers. So I did HSS sections, I chose weathered steel, that way we can give it a really nice industrial look, and also there's no maintenance involved with weathered steel. You don't have to paint it, so we don't have to worry about that, and it gives it a really cool vibe. And also the bridge deck, I designed corner decks around the elevator, so like there'll be a deck connecting the elevator eventually, but there's decks so that way people can, like we can set benches on there, people can wait for the elevator, they can kind of hang out there and look at the cars going through the roundabout and things like that. And I'd like to introduce the geotechnical report.
Okay, now let me introduce the geotech design. For the design criteria, all the foundations were designed to follow ACSE 7 and ACI 318R14 design code. And a factor of safety of 2.5 was used in this design. And the designed foundation will not settle more than 1 inches. And also angular distortion and bearing pressure were considered. The angular distortion is the difference settlement between 2 foundations. related to the spacing. And the bearing pressure of soil is its ability to carry load of structure without excessive settlement. Also, for the pavement design, it will follow the INDOT design manual and the ASHTO guide for design of pavement structure. Here is the final geotech design for the bridge system. A total of 16 spread footing will be used in the bridge, and 4 mat foundation are required for the elevators. For the constructability, all the spread footing will design made the same size, and all the mat foundation were designed made the same size. Spacing between the spread footing to mat foundation will be 54 inches. For the spread footing design, based on our structure engineering's assumption of the structure load, the dimension required for the spread footing will be 5 feet long by 5 feet wide. And the depth of footing will be 20 inches, and the column will be 4 feet. This size footing results in a total settlement of 0.85 inches, which is within 1 inch settlement constraint. For elevators, we will purchase an entire elevator system. The elevator car will be 64 inches long by 64 inches wide, and the total equipment weighs 6,000 pounds. Also, this elevator, the maximum passenger capacity will be 13 people. Based on this elevator size, there will be around 226 cape force on each mat foundation. The dimension required for the mat foundation will be 9 feet long by 9 feet wide. Also, the depth of pit will be 62 inches, and the height of mat foundation will be 10 inches. That means the total height of this mat foundation will be 72 inches. Also, the thickness of the pit wall will be 10 inches. This mat foundation results in a total settlement of 0.95 inches for the mat foundation, which is within 1 inch settlement constraint. For the pavement design, we assume a 20 years design period, and a structure number of 3.8 was used in this design. Finally, we decided 2 inches HMA surface, 4 inches HMA intermediate, 6 inches HMA base, and 12 inches number 5-3 compacted aggregate base. Now let's pass Owen to introduce the water resource.
Thank you, William. So for the hydrology portion of this project, the primary goal was to use a low-impact design so that we could reduce stormwater runoff at the site as well as improve water quality of this runoff. Low-impact design is basically a design that naturally infiltrates, detains, retains, or evaporates stormwater with minimal impact on the surrounding environment. So in order to start this process, I first had to find how much water was draining into the site. I did this by getting some spot elevations and finding a contributing watershed, shown here in orange, of about 9.2 acres. Using this area, I was able to find the flood control volume, which is basically the amount of runoff to expect during a storm event that my system needs to be able to handle. Using the 24-hour 100-year storm event, I found a runoff of about 310,000 cubic feet. Then for the water quality volume, or the amount of stormwater runoff that needs to be treated at the site, I found a volume of 3,000 cubic feet, so a much smaller value. Moving into my selected design, I decided to go with a detention basin just west of State Road 49, shown here in blue. Along with this detention basin, I needed stormwater sewer pipes to take the stormwater from the site to the detention basin. Those are shown here in black. For the water treatment, I decided to go with pervious pavement, shown here in yellow, along the roundabout. And also to aid this, I proposed rain garden vegetation improvement to the south of the intersection, shown here in purple. So as for routing the water to the intersection, as I mentioned before, the orange area is the contributing watershed. I decided to go with 4 inlets, shown here as the circles in black. The water goes into these inlets, follows the storm sewer pipes to the detention basin, where it will either infiltrate into the ground, some will evaporate, and then the rest will drain in through another storm pipe segment into a current wet bottom pond to the north of the detention basin. As for my detention basin design, a few of the major requirements that I had to deal with in designing this were a max depth of about 4 feet and a 3 to 1 foot minimum side slope. I also needed adequate clearance of 10 feet between the 2 existing roadways surrounding the detention basin. From there, I went into storm sewer pipe design. With this, there were 5 concrete pipe segments. As you can see in this, there are 3 around the intersection, 1 leading to the detention basin and 1 more to the north. These segments totaled about 2,000 linear feet of concrete pipe. For each pipe, I had to design their own peak flows as well as sizing their diameters. These diameters of the pipes range from 16 inches to 36 inches. I also designed for the invert elevations as well as the design strength of each pipe so that it could hold the weight of the pavement, the soil above it, and the live load of the traffic that would be over the segments. The final major part of my design was pervious concrete sidewalks. I saw that I needed 1,200 linear feet of pervious sidewalk approximately. Based on design requirements, I selected a 5-foot width for these sidewalks, and then from there I used an Excel program to iterate for a gravel base depth that would prevent ponding during a 2-year 24-hour storm event. This Excel gave me a gravel base thickness of 30 inches, shown here in this graphic. Moving on to the project cost summary, on the table to the right, you can see each discipline's cost summary for construction and materials broken out individually. On the left, you can see our design cost of $115,000. That's based on an hourly fixed rate for design work that we decided on at the beginning of this semester. And at the bottom, you can see our total cost for the project at $9 million. To summarize, we went over the project introduction as well as each discipline gave their overall design report for the project as well as a cost summary for our project. Now I'd like to invite up my colleagues to answer any questions that you might have. Yes, sir.
Did you compare the existing level of service at this intersection to what would be anticipated roundabout?
It's currently at a D or C, I believe, right now, and with the new roundabout, because of the software that we have, instead of using a level of service, I calculated it based on a volume to capacity ratio, which was about 0.6.
Yes, sir.
Do you anticipate buying new right-of-way to build your project?
Yeah, part of our cost is definitely land acquisition. That's for both the transportation aspects and the stormwater aspects. We had to acquire land.
How much?
9 acres?
Yeah, 9 acres. Yeah. Absolutely.
Thank you for listening.